All right, guys, so today we are going to talk about using Kepler's law and how to apply Kepler's third law to different planets and different information in our solar system and in space. So please forgive me before I start. It's a lot of math work and I don't have enough room to write on it with dry erase marker. So I'm going to bring in a piece of notebook paper to write on. You definitely have plenty of room though to fit it all on this sheet of paper. My markers are just really bulky. So before we start, we need to look at this equation. We need to remember that K is our orbital period. Not K is our orbital period. K is Kepler's constant. T is our orbital period. I'm going to write the information for T in orange. So T is our orbital period. We're going to want that information in seconds because we're measuring an amount of time. R cubed, R is our orbital radius. It's written in blue. We're going to want that information in meters. So now that we've clarified what we're looking for, let's follow the instructions on the sheet. It says use Earth's data to calculate Kepler's constant for the Sun. Then calculate the missing values for Saturn and Venus. So here's the Sun. Here's our data for the Sun. And I'm going to zoom in a little bit so we can see that data a little bit better. Maybe I'm not going to zoom in. It's not going to let me. All right. So we know from our notes yesterday that the equation for Kepler's third law is the orbital period, or the Kepler's constant for the Sun, is equal to the orbital period of Earth squared divided by the orbital radius of the Earth cubed. So we're looking for Kepler's constant of the Sun. We know from our paper that the orbital period of the Earth, or T Earth, is 3,1,500,36549 seconds. And we want that to be squared. We also know from the givens that the radius of the Earth, or the orbital radius, is 1.49598 times 10 to the 11th. We want that cubed. When we do the math, we're going to come to the conclusion that the Kepler's constant for the Sun is 2.97 times 10 to the negative 19th seconds squared per meters cubed. So we've done this first one. Now we need to calculate the missing values for Saturn and Venus. So we're going to plug in what we have into those equations. Let's start with Saturn. So for Saturn, we have the orbital period and we're looking for the orbital radius. My equation is Kepler's constant for the Sun is equal to the orbital period of Saturn squared divided by the orbital radius of Saturn cubed. When I rearrange this, because I'm solving for the orbital radius of Saturn, I'm going to bring this out. I'm going to get the orbital radius of Saturn is equal to the cube root of the orbital period of Saturn squared divided by Kepler's constant for the Sun. I'm going to plug in what I know. So the orbital radius of Saturn is equal to the cube root. The orbital period of Saturn is 928959105 seconds. I want that to be squared. I want to divide that by Kepler's constant for the sun, which is right here, 2.97 times 10 to the negative 19th seconds squared per meters cubed. When I do the math work there, my orbital radius for Saturn is going to come out to be 1.43 times 10 to the 12th meters. My seconds squared are going to cancel. Last but not least, up at the top, we need to figure out the orbital period for Venus. So Kepler's constant of the sun is equal to the orbital period of Venus squared divided by the orbital radius of Venus cubed. I know a lot of y'all just like to plug in what we have, so we'll work that one this way. Kepler's constant of the sun, we discovered on the first page, or before I flip my page over, was 2.97 times 10 to the negative 19th seconds squared per meters cubed is equal to, we are looking for the orbital period of Venus over, we know the orbital radius of Venus is 1.08208 times 10 to the 11th meters. I'm going to multiply this out and then take the square root of this side. My final answer is going to be the orbital period of Venus is equal to 194,00572.3 seconds. All right, the bottom half of this worksheet is going to be the exact same as the top. So it says Galileo Galilei discovered Jupiter's 4 largest moons in the early 1600s, shortly after the invention of the telescope. Use Io and Europa's data to calculate and confirm the Kepler constant for Jupiter. Then find the missing values for Ganymede and Callisto. So what you're going to do is the same thing that we did up top. So you're going to use the givens for both Io and Europa, and you should come up with the same answer for both of those for Kepler's constant for Jupiter. Once you get Kepler's constant for Jupiter, you're going to use that information to solve for the orbital period of Ganymede and then the orbital radius of Callisto. If you have any questions, feel free to send me an email or contact me and I will get in touch with you.